We're checking out the source code to OpenFOAM, which is some sort of physicsy simulator for fluid simulations. I think numerical solvers for fluids, something along those lines. I am expecting it to be mathy and probably partial differential equation-y, and that's really all I know about it. I have seen some videos of OpenFOAM in action. It looks super cool, but I just don't know much about how it's used or what's up. I don't know if it's used for special effects or if it's used for science, but that's what's the deal. We have some user guide here, C++ source guide. That's just the generated code. It does have a Wikipedia article. It says it's for development of customized numerical solvers and pre/post processing utilities for the solution of continuum mechanics problems, most prominently including computational fluid dynamics. It's used in research organizations, academic institutions, and across many types of industry. For example, automotive, manufacturing, process engineering, and environmental engineering. Yeah, we get a video. So here's some simulation. Maybe there is a video we can watch. And so there's some training. Here's a bathroom toilet. Should we watch this? Sure. Let's do it. This looks short. So I guess this is some simulation in OpenFOAM. You've got the water in the tank. I guess it's starting to flush because we see the water is flowing down here. Accumulating in, maybe that's a P-trap. I don't know if that's officially called. I guess we're getting it rotating. I don't know if you model this mesh in OpenFOAM or you import some modeled mesh from some other thing like Blender. And that's, I don't know what the red, the blue, and the green are. Maybe maybe it's like the amount of turbulence or something along those lines. Okay, so that's what OpenFOAM is for. And let's dig into the code. I'll set a timer, 30 minutes. As I've mentioned in my other videos, we are sprinting to the end of the current request lists so that we may enter a new regime with a better, I think, approach to handling requests. But these are the requests that I promised that I would get to. And I want to make sure that I live up to my word. And so this one was requested on Reddit, I think. The only Reddit request that I've gotten. Okay. And if you want to, people ask me if they can request new videos. The way to do that right now is to join the Discord. You can find the link to the Discord on the video description. And on the Discord, we have a spreadsheet of potential requests, kind of a brainstorming spreadsheet, and that will seed the process for having the community choose kind of which requests to prioritize. But the status right now is I'm not taking new requests, but I will record the interest in a particular repo or a particular topic in that spreadsheet. Okay, so here's some bug just flew directly at me. All right, so here's the source file. We have ODEs, which should be ordinary differential equations. We have some sort of POSIX stuff. We have OpenFOAM, a P stream, which is, I guess, relevant because we just watched the toilet. We have thermophysical transport models. I'm assuming that it has to do with transport in general. I don't know if thermophysical is the same as thermodynamic. We have atmospheric models. That's probably related to climate. Hello, friends of birds. Hello. I don't know what friends of birds means, but I support it. Combustion models, conversion. I don't know what we're converting. That might be something boring like file formats. That might be converting one sort of physical model to another. We have agglomeration methods, constraints, mesh distributors. FV. I don't know what FV stands for. Mesh movers, mesh stitchers, mesh topo changers, models, motion solver. So these FV things look like the sort of stuff you would see in Blender. They look like ways of dealing with and modeling 3D meshes. We have generic. I don't know what generic means. Lagrangian is either for computing with Lagrangians or dealing with a Lagrangian equation. We have mesh, which I'm going to guess is maybe the main model for mesh is like the base model. Then we have mesh tools and mesh check, which I'll ignore. Motion solvers, multi-phase models. Parallel is probably for parallel processing. Physical properties, that could be any number of things. I'm guessing that's just possibly attaching physical properties to the mesh. We have radiation models, topo changes, random processes, renumber, rigid body motion, sampling, species transfer, which sounds unnatural. A surf mesh is probably a surface mesh, thermophysical models, a tri-surface, maybe triangular surface, two-phase models, and waves. So this is way too much to get to. How are we going to start? I guess let's start with ODEs. We'll pop this out. I have a feeling ODEs might explode. We have solvers and systems, which is more interesting. We have the Euler solver in Euler SI. This might be familiar with, I guess, those of you who've used Stable Diffusion. They use the Euler solver sometimes. I don't know what ODE solver on its own is. This is probably some well-known solver. We get the OpenFOAM documentation. A fourth order Cache-Carp Runge-Kutta ODE solver. So I remember Runge-Kutta from ODE class. And this is, I guess, the cache and carp probably improved on Runge-Kutta, which I think is super old. When is Runge-Kutta from? In numerical analysis, the Runge-Kutta methods are a family of implicit and explicit iterative methods, which include the Euler method used in temporal discretization. These methods were developed around 1900 by the German mathematicians Karl Runge and Wilhelm Kutta. Okay, so 1900. Wow. All right, so all of this arcade stuff is probably, must be Runge-Kutta stuff. Trapezoid is probably the trapezoid method for like numerical integration. Adaptive solver is probably some sort of attempt to do a smart solver. And I don't know what Rodas are. Rodas and Rosenbrock. How about Rodas method? Construction of a multi-rate Rodas method for stiff ODEs. And then this just must be these must be, I don't know when to use these various methods. I guess we'll just pick out a couple of the methods, and then did we ever open the system? So ODE system, we just have the header and the C file, which for some reason is capital H header and capital C code. Why? I don't know. This is just some copyright statement. And oh, look, we got a useful description as part of the copyright template. That's outstanding. So the class is foam : ODE system. And the description is it's the abstract base class for systems of ordinary differential equations. So what do we need? We need to know what the variables are. And we need to know what the equation is. And I guess what field we're in. Presumably over real or in complex fields. Not any sort of fancy prime fields. And we have this check thing, which is, I guess, doing some sort of check stuff. You can create an ODE system. And it's a system of equations. So you can have some number of equations. We have this virtual void derivatives. Calculate the derivatives in dy dx for the current state x and y. An optional index for the list of systems to solve Li. I don't know what Li is. We can calculate the Jacobian. which is basically just the matrix of second derivatives. And that's what we can do. Do we get PDEs? We have P delta. I guess, is it just too hard to solve PDEs? Let's try OpenFOAM PDE. Solving PDEs with OpenFOAM PDF. So the PDEs we wish to solve involve derivatives of tensor fields with respect to time and space. So what? There's some tensor stuff, but where do the... So we have equation discretization. So it converts the PDE into a set of linear algebraic equations where ax equals b and x and b are the vol fields. FVM is finite volume method. So I think we saw a bunch of FV stuff. That's probably finite volume solver. Let's ask the AIs. So OpenFOAM, the OpenFOAM source code has ODE solvers. And it so why only on ODEs and not PDEs? I think I'm probably missing something fundamental, like approximating the PDEs with an ODE. OpenFOAM's core functionality deals with solving PDEs related to fluid dynamics and heat transfer. Here's why. There are a couple of reasons why they might include ODE solvers, so submodels within PDE solvers. Many CFD simulations involve submodels. Standalone ODE simulations. Okay. I don't know. Maybe we will see some PDE stuff. Maybe I'm just missing something, which is usually the case. Okay, so let's just take a quick look at some of these solvers. We have 20 minutes left. Okay, so maybe I'll also look at the system. There's a nice lambda, or nabla, I mean. Okay, so this check thing is going to evaluate the derivatives using the derivatives method, etc. I'm guessing just numerical derivatives, right? It's the only thing we implement is check, right? We've got check and what? Okay, here's df dx 0. I'm not really sure what's going on. Let's see if we can find other references to df dx. With this function derivatives, we go there. Let's try Emacs. Where we source ODE solvers. ODE system, right? Okay. So possibly defined in chemistry model. So derivatives takes a time, which is a scalar field, a label, Li, I guess Li is the label, and a scalar field, dyt pdt. And we do what? We check if we are a reduction. And then for all s talk I, we're going to set y stock of I to the max of ytpi, else we'll do some stuff for y. I don't know really what's going on. We have some rho m thing evaluating a mixture density. I don't know if that's mixture density in the sense of a probability thing. Species thermos. Something. Some sort of, we're looking at reactions. Right, I'm not sure. I'm not sure what's going on there. What about this df dxe thing? No definitions for that. What about scalar field? We have primitive fields. We have, okay, so these are, a field of scalars is a scalar field. That makes sense. What is a field? We have field.c. A field is just like a list. Okay. That tells us a little bit, but I feel like I have more questions than I have answers. Let's return to solvers. That's ChatGPT. That's Emacs. I think this one. Okay, so ODE system doesn't seem to have much there. Actually, let's open that back up. Oops, not that. And let's see if we're importing anything, including ODE system.h. I guess this gets implemented somehow as other things. So the ODE solver Euler.h has what? We have a type name, Euler. We can construct one, we pass it in an ODE system in a dictionary. I guess the dictionary maybe has the like values of the variables or something along those lines. Inherit from the ODE solver. Resize the ODE solver, I don't know what that means. And then we have this solve thing. Solve a single step dx and return the error. So we are going to, oh, these are just we're in the header, so this is just the arguments to solve. And so on. So let's see what the implementation looks like. And solve will, for all error underscore I, calculate error estimates from the change in state. So we're going to take dx, multiply by dx, sorry, dy dx0 at I. I guess dy dx0 is a vector, or I guess it must be a vector. It's not a matrix. And that's going to give us an error underscore at I. And then we'll update the state by setting y sub I to equal y0 sub I plus error at I. And then we will normalize the error. And then that's what? That's Euler solve taking in a bunch of arguments. Is this just fewer arguments? We call adaptive solver here. If we pass it in what? I'm not sure. So it looks like we're maybe passing in less stuff here. And we're using adaptive solver as opposed to the Euler solver, although this is Euler. And in this solve function, we are passing in dy dx as a scalar field, which is just a list. And so all the stuff we need for calculating this stuff is passed into the function as opposed to being computed by the function. Okay, fair enough. And then here's the generic ODE solver. I don't know what solver L is. An abstract base class for ODE system solvers. And what? We have some ODEs. We have abs to L, absolute convergence tolerance per step. So this is somehow configuring, I think, the convergence. And we have a step state, which is a class, although it's started in lowercase, which is a little bit unconventional, but it doesn't matter. And we have a Boolean for forward, maybe whether this is a forward step as opposed to some other kind of step. We have dxtry. I'm not sure I'm not sure what this T stuff is. This is some change in X, T or Y. I'm not sure. DID, I'm not sure. And then first, last reject, pre-reject, I guess with it to reject the state. And then step state called on a scalar dx. Okay, so we're going forward if dx is bigger than 0. And oh, dx try and did. Maybe I was thinking of this as something in the physical model, but I'm wondering if this is like we're going to try this dx. This is the dx that we ended up with, perhaps. And then whatever this first, last reject stuff is. Let's look at the implementation. That's resize. This is what? Sort of constructor it looks like. So solve of x, y, li, dx try is going to, we're going to call step on dx try to get a step state. We're going to solve with oh, maybe this, I'm not sure what's going on here, but we're passing in, I think we're passing in the thing we did here to solve. Then we're setting dx try to be whatever is in step dx try. Where's the step function? Let's head back to Emacs. No definitions for step. So we have step state, step.dx try. I'm not sure what step is supposed to be, like what type it is. I guess steps, we're just declaring the step is of type step state, right? Yeah, okay. So it's some state. And here's the solve thing. So we're creating this state with whatever dx try is. We're going to set x to the start, x start, and then we're going to iterate over the labels. I guess we're going to iterate over steps. So end step is 0. Well, this is confusing. This confused me. This is just checking if end step is less than max steps, but it looks like this is the beginning of like a templating thing. And then we're incrementing end step. I don't know why we're using a label. We're going to store the previous iteration, dx try. That's going to be dx try 0. 0 I thought would have meant initial, but this just seems to mean previous. We'll set step reject to false. Check if this is a truncated step and set dx try to integrate to x end. So if x plus step dx try minus x end times x plus step dx try minus x start is bigger than 0, then we'll set step last to be true. So I guess we were at the end. And dx try is the difference between x end and x. And then we'll integrate as far as possible up to step dx try, calling solve on x, which we maybe adjusted here, and step and li, which I think is some label. They're calling it a label, but I think it's an index into something, into what, I'm not sure. Maybe into which equation in the ODE. Maybe check if we've reached the end. We'll set step first to false, and if we reject, we set step previous reject to true. And there might be some error. Okay, so that's some implementation of solving. I find that I'm a little bit not used to the style of C code, so I'm getting a little bit mixed up on the syntax here. All right, so what else do we have? So that's IDE solver. It kind of looks straightforward from a numerical solver point of view, modulo me getting confused about the syntax and whatnot. This is the root directory. We don't need that. This is some directory we don't need. pstream. I'm not sure what pstream is. We have MPI. And this make and clean, I'm going to guess, are like new make files. These are scripts. WMake is maybe some make system. Maybe specific to OpenFOAM. MPI, I think, is the message passing interface for like high performance computing. UPstream. Valid parallel options vary between implementations. So this is like use parallelization for solving, I guess, some of these models. Thermophysical transport models. Let's pull this into its own tab. We have fluid, coupled thermophysical transport model, fluid thermo, phase fluid, multi-component thermo. These, I don't know how all of these differ. With any like scientific enterprise, there's going to be like closely related models with slightly differing assumptions depending on the problem you're trying to solve. I don't know the extent to which the names that they've chosen are like industry standard names, or if they're just kind of like custom OpenFOAM names as they're trying to figure out where each thing goes. Here we are in fluid, and we have laminar, which is like, I'm guessing, modeling a fluid with laminar flow, turbulence, presumably modeling a fluid that has some turbulent flow. Phase, thermophysical transport model, derived FV patch fields, and so on. We'll just peek through some of these and try to get a sense for what is life like as an OpenFOAM developer. Fickian Fourier. So this is laminar. Maxwell Stefan. Let's look up Fickian. So this is related to Fick's laws of diffusion from 1855. So there's some diffusion coefficient. The first law, movement of particles from high to low concentration. Diffusive flux is directly proportional to the particle's concentration gradient. And the second law, prediction of change in concentration gradient with time due to diffusion. Okay, so this is classic stuff. Fourier. I'm sure Maxwell Stefan is maybe James Clerk Maxwell. This seems to be, I think we figured out laminar flow much earlier than turbulent flow, which I don't think we've figured out even. I think is in general an open problem. So we have some eddy stuff. Eddies are little turbulent curly things, and so on. This is turbulence. Here's fluid in general. We have a phase thermophysical transport model. Let's look at that. It's a templated base class for multi-phase thermophysical transport models. I don't know what multi-phase means. I don't know if we're like changing like phases of matter, or if we're maybe changing from laminar to turbulent, or both, or all three. We have a momentum transport model, a thermo model, and a momentum transport model alpha field. We have some constructors, and I don't know. Let's look up thermophysical transport model. We may end up back in OpenFOAM. Thermophysical models. They are used to describe classes where thermal energy, compressibility, or mass transfer is important. OpenFOAM allows thermophysical properties to be constant or functions of temperature, pressure, and composition. Thermal energy can be described in form of enthalpy or internal energy. The relation can be described with various equations of state or as isobaric system. The Thermophysical Properties Dictionary is read by any solver that uses the Thermophysical Model library. A thermophysical model is constructed in OpenFOAM as a pressure-temperature system from which other properties are computed. There is one compulsory dictionary entry called thermotype, which specifies the complete thermophysical model that is used in the simulation. And so this seems to be, let me see if this is any more readable without Dark Reader. Sorry for the brightness, and no, it's just about the same. But this looks like maybe this is generated documentation. And so this is useful. I guess this is probably all in the code as well. We have some equation of state is an with an ICO polynomial, which is an incompressible polynomial equation of state, e.g. for liquids. So it's polynomial. I forget what incompressible means at the equation level. Perfect gas is a perfect gas equation of state. I don't know if these are two types. Then we have basic thermophysical properties like a constant specific heat model. Or maybe these are types of models. I'm not really sure what we're listing here. Various combinations are available as packages specified using, for example, thermotype. Type is E-rho thermo. Mixture is pure mixture. Transport is const. Thermo is H const. Equation of state is perfect gas. Species is species. And energy is sensible enthalpy. And then we have a mixture, which I guess is setting species to mole, maybe molecular weight, 28.96. Thermodynamics, CP and HF. I forget what they are. I guess these are, I don't remember. And transport, mu is 1.831 times 10 to the negative 5. And PR, maybe pressure, is 0.705. So these are ways of, oh, here we go. Species containing, i.e., number of moles and moles of the species and molecular weight in units of grams per mole. So mole is the moles as opposed to the, so mole weight, I guess, is the weight of a mole as opposed to the molecular weight. Thermo is containing coefficients for the chosen thermodynamic model. Transport is containing coefficients for the chosen transport model. Thermodynamic coefficients are ostensibly concerned with evaluating the specific heat. Yeah, so that's what this was, right? Somewhere. Or maybe not. From which other properties are derived. The current thermo models are described below. We have H const thermo, assumes a constant Cp and heat of diffusion, and a heat of fusion, HF, which is simply specified by two values, Cp and HF. E const thermo assumes a constant Cp and a heat of fusion. These are both constant in a heat of fusion. Cv. I don't know if like Cp is like position and this is velocity. I don't know. Okay. So that's actually an interesting and useful page, but I'm not going to read all the way through it. I think we're technically out of time, but I'm going to keep going because I'd like to see some more of this repo just to understand a little bit about what we're doing. Here's derived FV patch fields. So what did we decide FV was like finite volume? Derived, I don't know if this means that we've taken a derivative or perhaps these are just derived in the sense that they come from some other patch field or finite volume thing. We'll just peek inside one of them at random. The class is this thing, external coupled temperature mixed FV patch scalar field. These names would make Java programmers envious, I think. And the description is this boundary condition provides a temperature interface for an external application. Values are transferred as plain text files where OpenFOAM data is written. So I guess we're using text files as a medium of transfer, and maybe that's related to using MPI. That means, I guess, if we interpret it totally literally, we're like writing to disk, which doesn't seem like the most optimalist thing, but I don't know if that's actually what we're doing. Provides a temperature interface to an external application. I'm not sure what that means. And we receive as the constituent pieces of the mixed condition. For example, value 1, gradient 1, value fraction 1. Data sent and received as a single file for all patches in the directory. So I guess this is a patch maybe of a model, of a finite element model and then we are sharing it with other nodes so that the different patches can be solved independently on different nodes in parallel and then stitched together, I think is probably what's going on. So let's see if we can pull up a diagram of the finite volume method. The finite volume method is a method for representing and evaluating partial differential equations in the form of algebraic equations. In the finite volume method, volume integrals in a partial differential equation that contain a divergence term. This is divergence in the calculus sense, I assume. Yeah. Are converted to surface integrals using the divergence theorem. These terms are then evaluated as fluxes at the surfaces of each finite volume. Okay. So we're just using the fundamental theorem of calculus, really. Because the flux entering a given volume is identical to that leaving the adjacent volume, these methods are conservative. Another advantage of the finite volume method is that it is easily formulated to allow for unstructured meshes. It's used in many computational fluid dynamics packages. Finite volume refers to the small volume surrounding each node point on a mesh. This you can contrast with finite difference. So for example, consider a simple 1D advection problem. Given by that, blah, 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 integrating, blah, blah. That's all fine and good. That's math. What I'm more curious about is how this parallelizes. And I think I was implicitly confusing it with the finite element method. And in the finite element method, we subdivide the whole domain into simpler parts, having several advantages, blah, blah, blah. Let's see if this mentions finite volume. I mean, yeah. Generally, FEM, the finite element method, is the method of choice in all types of analysis in structural mechanics, that is, solving for deformation and stresses in solid bodies or dynamics of structures. In contrast, computational fluid dynamics tend to use FDM. I don't know what the D is here, or other methods like finite volume method. Okay, so what is FDM? Finite difference. Okay. So we're doing finite volume as opposed to finite element. That's all fine. And this somehow this patch scalar field is some way of cutting up the volumes, I think, and sharing them with other machines. Here's a fluid thermophysical transport model. This is the abstract base class for fluid thermophysical transport models, RAS, LES, and laminar. I don't know what RAS and, what was it, LES are? You use the class. And I think there's not much interesting in the header. Let's see if there's anything much interesting in the C file. Not really. You've got this label patch I, which I'm guessing the label, they use labels for like indexes. I'm guessing label is just typedef as like an int. Yeah, a label is just an int. So I guess we're just keeping track of which patch we're on. And so that's a thing we can share with other nodes. And what else do we have? So here's fluid thermophysical transport models. The names are all really similar. I don't know the difference between these two headers. Model versus models. One is plural. I guess probably the plural one is a container. So this file we get includes, so we're including some laminar models like Fourier.h and the Unity Lewis Fourier, and also RAS models like eddy diffusivity, which is what's the word? Non-laminar, turbulent, and also LES. I don't know the differences between all of those, but those are things that we're including. Here's fluid multi-component thermal. I'm going to guess that I'm going to guess that's not so informative. Let's look at this one. I'm going to guess this is similarly not so informative. These are type defs for laminar, RES, etc. These are all type defs. Is there anything in the C files? I'm finally getting a feel for like how the code is laid out. Okay, so these thermo whatever Jim will call it models are not so, these files are not so important. Just for the sake of thoroughness, let's check this folder. This is some new function that'll create one, some kind of model. And we've got an iObject IO dictionary header with a group name, some thermo mesh stuff, timing, must read, no write. If the header is okay, and we'll look up something in the dictionary, looking up the model. And I guess this is like, seems like we're working with a file. And we'll somehow grab an iterator and check if it's equal to the dictionary, constructor, table, pointer. End. I guess the end of the pointer. And if so, I guess we will error out because somehow the iterator got to the end of the thing it wasn't supposed to yet. It says unknown solid, thermophysical transport model. Otherwise, we'll return an auto pointer of phase solid thermophysical transport model, taking the thing we get from the caster iter and passing in alpha and thermo. So I think essentially we're reading some file and possibly also writing files. Okay, so no more models. I'm done with models. Here we are in Fourier. This is maybe actually doing some math. Fourier's temperature gradient heat flux model. Simple species laminar flow. Heat flux source is implemented as an implicit energy correction to the temperature gradient based flux source. At convergence, the energy correction is 0. So it sounds like when we have converged, the energy correction is 0. I don't know if energy correction 0 is how we determine whether we've converged, but maybe we will see it in the implementation. So we have some class Fourier, and this syntax is really throwing me off. It's extending some model. It's extending a laminar thermophysical transport model templated by basic thermophysical transport model. And we'll define some types. We'll declare what the type name is. You have a constructor, you have a destructor, and some member functions. Coef_dict is the dictionary of coefficients. You can read the dictionary, or that returns a bool. Maybe this is whether we can read the dictionary. The effective mass diffusion coefficient for a given species mass fraction is some temp. Why is it temp? I don't know, but some temp vol scalar field. Vol maybe volume. D, E, F, F. D, E are capitalized. Not sure why. And I'm not sure really what's going on there. We also have this other temp scalar field thing, effective mass diffusion coefficients. These are two coefficients. More temp stuff. Everything is temp. Why? I'm not sure. Let's take a look at the implementation and see if we just see anything interesting. So each of these functions, I guess, gets a fatal error function. I'm not sure if we're just setting the fatal error function so we can essentially return it or print it if an error happens. And yeah, I don't know. And then here, what is this? This is some model. This is some function Q, which is going to, which is templated. This should be the return value. It's returning some version of a model, and it's calling whatever FVC is, finite volume compute something, and we're interpolating with alpha times thermo.kappa times FVC SN grad. Grad, I'm going to guess, is gradient. SN, who knows? Passing in thermo T, and we're taking the negative. This is some group name. Maybe this is just metadata. And or rather, we're returning a scalar field with this is the second value. This group name thing is the first value. And the name of the thing is Q. So that's probably some coefficient in the equation. And so on. So there's like a mix of computation here and also like metadata and so on and so forth. I still don't know why everything is temp, but I don't know why a lot of things are the way they are. Maybe TMP stands for something other than temporary. Here's Maxwell Stefan. This should be pretty similar, I think, in spirit. We have an array of species binary mass diffusion coefficient functions, which are dfuncs. And then we also have DT funcs, which are the Soret thermal diffusion coefficient functions. I don't know what they are. I don't know what species is. Species fluid dynamics, or maybe it's about thermodynamics. Computation fluid dynamics. Okay, so single species means it consists of one chemical species. I don't know what a chemical species is. Chemical species are a specific form of chemical substance or chemically identical molecular entities that have the same molecular energy level at a specified timescale. These are classified through bonding types and relatively abundance of isotopes. Types of chemical species can be classified based on the type of molecular energy, molecular entity. It can be either atomic, molecular, ionic, or radical species. Table salt is an example of an ionic species that is composed of the chemical formula NaCl. Okay, so that's what a chemical species is. It's, I think, maybe from the perspective of this software repo, the species, the fact that it's one species tells you that it can be kind of modeled with similar equations. And then when you change species, it seems like you change maybe how you model it. This is more transport model stuff. I'm going to guess there's not much there. Eddy diffusivity. I'm just mildly interested in seeing whether this is different enough. We have some momentum transport stuff. We have rho and nut. I don't know what nut is, and we're dividing by PERT. I don't know what PERT is, but I don't think we've seen momentum really yet. Before, I don't think we've really seen much about boundary conditions either, although we may have, and I've just glossed over it. So this is some model, and we feed it a momentum transport model and a thermo model. And PERT is dimensionless, I guess, and we have some coefficient dictionary and some alpha T. And I guess the thing that we're defining alpha T as, alpha rho phi group, I guess it's like alpha at time T. And we have some, I guess we're passing in some momentum transport mesh. All right. This is more different models. Don't do that. And what, so we have some, so this is atmospheric models. I'm going to guess these are all kind of similar to look at code-wise. You have vector scalar fields. I mean, the thing that's going to be different about them are going to be that the ODE systems are different. The code is really going to look the same. Combustion models. There's lots of different kinds of models. No combustion, radiation, diffusion, combustion, PASR. Conversion. This seems to be for converting mesh stuff. I don't know what an agglomeration method is. Oh, maybe agglomeration is like stitching patches together. Pair patch agglomeration. Let's see if we can find anything about it. Primitive pair patch agglomerate method. Let's look in the documentation. So maybe it's a form of coarsening. Operation coarsens using agglomeration. This is what? This is the GAMG solver. using agglomeration, so face area pair, geometric and algebraic pair, numerical coefficient. Agglomeration, number of levels depends on number of cells at coarses level and hard limit of a maximum 50 levels. So I think we're maybe combining nodes in some way. Here's face agglomeration. Agglomerate boundary faces using the pair patch agglomeration algorithm. Writes a map of fine to coarse grid. So I guess you have the fine grid is the you have some mesh that's fine, and you're trying to make a coarser mesh, like a low. In graphical terms, it might be similar to making a low poly version, so that presumably the algorithm runs faster on the coarser version. Distro. You're asking me which distro this is? This is Linux Mint, I think. Yeah, Linux Mint. So this window manager is Cinnamon, if that's the question. All right, so that's what agglomeration is. This should be some algorithm for matching up faces of the mesh that are close to each other and combining them into a single face. This is constraints: limit temperature, limit pressure, mean velocity, force. Let's look at limit temperature. I don't know how these constraints are implemented, but we have some optional field, which is the energy temperature field name. The type is limit temperature. The phase is gas. Oh, this is just an example usage. Okay. So you can say that the phase of this object that you're modeling is gas. So we saw at the beginning a model of a toilet, which uses water, which is liquid. And I guess the minimum temperature here is 200 something or others, not Kelvin, probably Celsius, and the max is 500. And then I don't know what actually enforces the constraint. So the constraint function which is a Boolean, so I guess it's going to return whether you successfully constrained it. So we have a label UList of cells. Maybe this is like the UV decomposition. No, what's it called? Something. UV mapping. I'm going to guess something like that. I don't know if that's what the U is for. Uh-oh. I don't think I can get that back. I can. So we have the cells, and we check if the dimensions equal the temperature dimensions, I guess. If they don't, there's probably some error. No, we have some other algorithm that runs if the dimensions are not what we expect. And we get a primitive scalar field. No, we look at HE, which is the vol scalar field we passed in, and we get its primitive field ref. This is probably a pointer to some object contained in the vol scalar field. And for all of the cells that we got from the set, I'm not sure where the set came from, then we are going to take cells at I, taking this vector or container and taking this element, getting an element, and then setting here TC at cell I. I don't know why we needed to create a new variable. And we're going to set it to the maximum of, okay, so this is just clamping between max and min. Okay, so that's how it's enforced. And then if the dimensions don't match up, then we do something else. What do we do? I'm not sure. Where's the else condition? Else. You do some sort of mesh lookup group name. And we have a min and max field. And we have some boundaries, I guess, to consider. All right. Then we have mesh distributors, a load balancer. Maybe this is for distributed in the sense of we're distributing the computation. Dynamic mesh redistribution using the distributor specified in decompose pardict. CPU time. Yeah, so this is distributing, I guess, the meshes among nodes of a computer cluster, I guess, for solving. A mesh mover. We have inkjet, interpolator, motion solver. What is inkjet? Specifically for the pumping system of an inkjet injector. I guess this is for modeling the inkjet. And we have a motion solver. Maybe this is you give it the equations of motion or something along those lines. A motions, blah, blah, blah. Do you get a comment? Well, at any rate, a motion solver has, whether it's a solid body, an update function, some update the corresponding to the given map, some ability to change the topology. We have map mesh, update from another mesh using the given map. We can distribute, I think, in the sense of distributing to machines, and we can write. I don't really know what that does. Something about distributing in motion. We have topo changers. I'm going to just really plow along. There's nothing interesting in the make file, is there? No. Okay. Displacement. Let's look up OpenFOAM motion solvers. I just kind of want to know what they do. Standard solvers. Based on solving the cell center solid body rotation stress equations for the motion displacement, the model calculates the necessary rotation to align the STL surface with the closest mesh face normals, and it calculates the respective source term for the SBR stress equation. So I'm not sure if this is for like internal use for OpenFOAM to figure out like the physics by rotating the mesh and solving stuff about mesh rotation, or if this is for modeling objects using the equations of motion. So we get some inheritance diagram, and I'm not sure I don't think there's enough here in the documentation to tell that to me quickly. Here's generic. We have generic fields, generic patches, generic field base, generic point base. And so we're way over time, so I'm just going to see if there's anything that I really want to see. So Lagrangian, this seems like maybe a pretty fundamental thing. A parcel, what is a parcel? I'm guessing it's a piece of a mesh. Include derived templates, parcel packing models, parcel injection models. I don't know. Clouds, templates and derived. So a colliding cloud, a spray cloud. Let's look at spray cloud. Spraycloud.h. Templated base class for a spray cloud. Submodels, atomization model, breakup model. We have a cloud type. The type of parcel the cloud was instantiated for. References to the cloud submodels. We have an atomization model and a breakup model. So I guess this is how things are atomized and how things are broken up. And we can construct the spray cloud. Let's look up OpenFOAM Lagrangian. This is Lagrangian solvers. So Lagrangian solver. What is a Lagrangian solver? I think Lagrangian is the kind of equation and not the kind of solver. Lagrangian function used to maybe using Lagrange multipliers used to solve constrained minimization problems in optimization theory. The Lagrangian submanifold in symplectic geometry. I don't think it's that. Lagrangian system, a fiber bundle, and Lagrangian density. I don't think it's that. Lagrangian in physics. Oh, this is maybe, yeah, the physical Lagrangian. I don't know if it's the field theory Lagrangian. No, it's just, the field theory Lagrangian is just the field version of the Lagrangian mechanics. I'm guessing this is maybe Lagrangian in the sense of Lagrangian mechanics. That we specify a Lagrangian physical system. A transient solver for compressible turbulent flow with coal and limestone particle clouds. An energy source and combustion. More. Do we not get more? Here's the source code. Limestone parcels. So parcel, I guess, is some like collection of volume containing limestone or something along those lines. We have a pressure velocity PIMPLE loop, corrector loop. And while the loop is going, we do includes. And while it's correct, we do more includes. And if the turb core, I don't know if this is like I am guessing turb means turbulent. Core, maybe correlation or correction. Oh, okay, maybe correct. So turbulent, then we call turbulence correct. And we set row to thermo row. We call runtime right. And we call print execution time. So this looks like it's actually doing work. We looked up Pimple before. Let's see if I can remember what it is. I don't remember. Is it pointer to implementation? Okay. The technique used for separating implementation from the interface. So we have the forward declaration of the implementing class, and then the const forwarding pointer wrapper, unique ownership opaque pointer, and so we're wrapping a unique pointer to the the forward declared implementation class. Because private members of a class participate in its object representation, affecting size and layout, and because private member functions of a class participate in overload resolution, any change to those implementation details requires recompilation of all users of the class. Pimple removes this compilation dependency, changes the implementation to not cause recompilation. Consequently, if a library uses Pimple in its ABI, newer versions of the library may change the implementation while remaining ABI compatible with older versions. Okay, so that's useful to know, and that's what's going on. Okay. So that's Spray Cloud. I feel like the Lagrangian folder so far is where all of the action is. Unfortunately, we are just way over time, and I'm going to just get out of here. So this is mesh stuff. We haven't looked at any of the mesh stuff. We looked very quickly at mesh solvers, but we're not going to do that. And we have multi-phase models. We'll ignore that. Parallel processing, I think, is probably about processing over different machines. Physical properties we haven't looked at, but we have viscosity, physical properties as a folder on its own. And there's not much there in the header. Thermophysical properties IO. I don't know what that is. I don't really see a list of like which properties we're dealing with. I don't know why viscosity gets to be a physical property, but like temperature doesn't. But that's what that's what's going on. And we have some model of viscosity with new. I don't know really what this is presumably related to the viscosity equation. I don't know much about viscosity or really any of the physics stuff here. Now we have polytopo change. This is something about changing the properties of the topological whatchamacallits radiation models. Scatter model. You know what? I was originally thinking this was like radiating like out from the center, but I think this is like radiating in the sense of electromagnetic radiation. But maybe we can take a check. This is the top level model. We have some scalar fields, a dictionary, a solver stuff. Declare runtime selection radiation model. I can't really tell. Random processes. K-mesh, OU force, FFT, maybe fast Fourier transform, noise, and turbulence. So those are all random processes. You probably literally need a random number generator for it. Rigid body motion should be just three-dimensional motion that doesn't deform the mesh. We've seen some of that in game engines. Sampling is sampling, but we're not going to look into it. Species transfer. I don't know enough about species to know what they're going to do there. Here's thermophysical models, which we've seen lots of models, and I don't think that they're super informative. Error loading page. About mass fractions. Yeah, okay. The tri-surface is some sort of triangulation surface. A two-phase model. We have things like compressible cavitation, compressible two-phase, interface compression, two-phase mixture. I'm guessing phase is maybe like, I don't know what VOF is. Is maybe like phases of matter, or where the physics change so fundamentally from one thing to another. We also have waves, which we're going to ignore. Random processes we'll ignore. Noise, I think we just opened up, but we're going to ignore. VOF has something to do with alpha controls. There's VOF physics. Or maybe VOF OpenFOAM. The breaking of a dam. So VOF method. Volume of fluid method is a family of free surface modeling techniques. That is, numerical techniques for tracking and locating the free surface. They belong to a class of Eulerian methods that are characterized by a mesh that is either stationary or is moving in a certain prescribed manner to accommodate the evolving shape of the interface. They're advection schemes capturing the shape and position of the interface, but are not standalone flow-solving algorithms. The Navier-Stokes equations describing the motion of the flow have to be solved separately. Okay. So free surface modeling, I'm not sure what exactly that is. They're numerical. Locating the free surface or the fluid-fluid interface. Okay, so I guess we have two fluids and there's some interface between them and it's moving over time perhaps. And we're trying to figure out like where it is. So I don't know what this is. Maybe these are two. This is, I guess, a ball dropping into a fluid. And then it makes a splash. This is a splash, I believe. So free surface modeling is the numerical modeling of a free surface, a freely moving interface between immiscible fluids. Okay. So zero parallel shear stress, such as the interface between two homogeneous fluids. Okay. So two immiscible fluids, and they make some sort of boundary or surface with each other. This is compressible cavitation. I'm not sure this is really going to learn anything from here, although we have Merkle. I doubt this is the same Merkle as the cryptographic Merkle. Merkle cavitation model. I'm just curious. Let's just open up a PDF. We're not going to get the whole full PDF. Evaluate the applicability of mass transfer cavitation models. Cavitation is like the creation of a cavity, I think. Cavitation in fluid mechanics and engineering normally refers to the phenomenon in which a static pressure of a liquid reduces to below the liquid's vapor pressure, leading to the formation of small vapor-filled cavities in the liquid. When subjected to higher pressures, these cavities, called bubbles or voids, collapse and can generate shock waves that may damage machinery. You don't want that. Okay. So that's what cavitation is, and that also explains why we want to solve for them in OpenFOAM. So that's OpenFOAM. I'm not going to look at OpenFOAM anymore. It's clearly a cool project. My only take on the code is that there's so much of the code is like bookkeeping. It was kind of hard to find where the physics is. In the times when we did find the physics, you would only see like a little bit of physics, and then you would probably have to like chase it down, and it's just kind of uh, it's not organized in a way that really makes, I think, reading it super easy. There may be reasons for that. It may be that that's that I don't know what the reasons would be, but it could just be that this is a project that kind of spans between the academic world of physics and to some extent numerical computation, and and industry. And so a lot of cases code like that is written in a very different way than you would see like in industry. So it, to me, it would be nicer to have like a clearer separation between like, here are the physical models and here's like the code for that we need for spreading out computations and having like real clear places in the source code for where to find those things. Um, because for example, if you wanted to like make a change to how um, like a if I wanted to make an optimization for some solver, it's not entirely clear like at what level to make that optimization. It seems like I might have to dig through a bunch of different things. It's not clear if the optimization can change depending on the model. Like there might be some types of physical models where you want to tweak the solver one way, whereas in another type of physical model, you want to make a different optimization. I don't know if that's um, a useful thing to do, and if it is, I don't know like how possible it is with this code base. I found it a little bit disorienting from a reading point of view. Some of that might be less disorienting if I were more familiar with computational fluid dynamics, but it just seemed to me like we were 95% of the time kind of looking at metadata as opposed to behavior. It's just my sense. And Raju is asking me to give them $9. No, but if you want to give $9 to the Holy Hedge Fund, you can do that through the YouTubes. Okay, so we've been live for a while. Two hours, 40 minutes. Part of me wants to do one more